All right, guys, here we go. Lesson 821 for geometry. Make sure for this lesson you guys have your books open to 821. You're going to need your books. And also, you should have gotten the resource pages passed out as long as some scissors. And you guys can start cutting out these flags. So make sure you have that done before you start this video. So each team should have I believe each team should have 2 copies of the big flags that say 3 feet and 4 feet. Each team should have 2 of those and cut those out. And then 1 page of the smaller ones. And there's like the different sets. So just make sure you have that cut out before you start this, and make sure you are on 821. Okay. All right. So once you have those cut out, I want you guys to kind of go through this problem here. So in the books, just kind of read through the problem. Have one person read for a bit and then switch to another person. Okay, answer A through D. Okay, and just do what it tells you. And really, guys, kind of focus here and get through this problem, then we'll go over it. Okay, I'm estimating around 10 minutes. So take 10 minutes, work through this problem, pause it here, and then we'll resume when you're done. All right, so let's go ahead and talk about this problem here. So for that first problem, we talked about Archie's version, and then we enlarged it to be 3 feet tall instead of 1.5 feet tall. So something I always recommend doing is labeling up your drawings. So this was the 1 foot one, and it was, I think it said it was 1.5 feet tall. So if we measured that height, it was 1.5 feet. Okay, so we had that. And they were wanting it to be instead 3 feet tall. So if you measure this, this is 3 feet. Okay, and we wanted to know what the width would be. We want to know what that is. So if you guys remember back from similar triangles, since these two are, this is an enlargement, it's going to be similar. All the same angles, just a different size. So it's a dilation, right? So if we look at our scale factor here, we went from 1.5 to 3. So to find your scale factor, we can just do 3 divided by 1.5. That's how you find your scale factor. You just divide your 2 corresponding proportional sides. So 3 divided by 1.5, that gives you a scale factor of 2. So that number right there is your scale factor. Okay, and we're really going to be using this term a lot today. So scale factor is going to be really important. So our scale factor is 2. That means going from 1 foot, we got to multiply that by 2 to get 2 feet. So our flag width should be 2 feet. Okay, so that was 1 times 2. That's how we got 2 feet. All right, so that essentially means we enlarged it by a scale factor of 2. All right, now part B, it was saying if you used $2 worth of cloth to create this model, how much cloth would it cost for the full-size flag? So most of you probably would have guessed $4, right? If this flag over here cost $2 and we used a scale factor of 2, then this flag should cost $4, is what we would think. Okay, so we're going to say $4 because our scale factor is 4. So you can write your original here, or you can write your explanation here. Okay, so now once you get to part C, now it's asking you to think about it a little bit differently. Okay, it says, how many scale versions fit into the larger version? Well, if you picture that, I drew a picture of it here. So if we look at our 1 foot flag and our 2 foot flag, you can actually fit 4 of the 1 foot flags inside of the 2 foot flag. So to answer that question there, this is going to be 4. So now if we think about that, if this flag here cost us $2, right, that was a $2 flag, then should this one really cost $4? No, it should cost $8, right? 2, 4, 6, 8, because that's the amount of, you're not paying for the scale factor, you're not paying for the width of the flag, you're paying for that whole amount of cloth. So this should really cost $8 because you can fit 4 flags inside there. Okay, so the cloth cost for the flag should actually be $8. So our prediction, if you predicted 4, was wrong, which is totally fine. Okay, that's what we want in this case. We're learning here, so we should have $8 there. Kind of an interesting thing, which leads us into our next part of our lesson. So now it's asking, what would the cost of cloth be for the flag 3 times as big? Okay, well, using that same logic there, if we looked, so now you're not just going to take 3 times 2, right? Our cost of this was $2. Scale factor of 3, you're not just going to take it times 3. You got to think about it bigger picture, okay? If you took the small triangles and you tried to fit them into the 3-foot triangle, you should have found that 1, 2, 3, 4, 5, 6, 7, 8, 9 fit inside of the 3-foot triangle, okay? So that means the cost should be 9 times as many, okay? So for part D here, if we have $2 for each of those flags times 9 of them that fit inside, that's really going to give us a price of $18 is what you should have for that first part of part D. And then finally for the cloth, for the flag that's 4 times as big, okay, if we look at the 4-foot flag, now you'd have, I believe it's 16 triangles that fit in here, okay? So we have another 16 triangles. So you got $2, but we're not just taking that times 4, we're taking that times 16 because we're paying for all of that cloth. Okay, so 2 times 16, you should have 32 for your price there. Okay, and it's already got the dollar sign there, so you don't have to write it. So 32. All right. So kind of a weird thing that's happening here. Now this is based on the area. So that's why we're talking about the area ratios of similar figures. It may not be what we think. If the shape is 2 times as big, our area is actually going to be even bigger than that. Okay. All right, let's take some data for number 68. So go ahead and move on to number 68. And it wants us to write down any observations or patterns that we found while working on the last problem. So what I want you guys to do is I want you to fill out this table here. So for that first triangle, okay, so if we look at our table here, if our side length, our width was 1 foot, the number of triangles we had, we're just going to put 1 here for this first one. And then when we increased that by a scale factor of 2, so we made it 2 feet wide, now we had 4 triangles that fit inside here. Okay, I want you guys to just pause the video, take a minute. It shouldn't take you very long, just 1 minute, and fill out the rest of this table. Really try and figure out what you're going to put in this. Figure out what the pattern is that's going on here between our width and our number of triangles. So just take a minute, fill out the rest of this table. Go. All right, so hopefully you paused it. You should have 9 triangles for this one, 16 triangles for that one. So if anyone figured out the pattern here, we are taking our width or our scale factor, these are our scale factors essentially, and we are squaring them. Okay, if you look at this, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. R squared is just going to be, we're just going to write that as R squared. Okay, whatever your scale factor is, you're taking that scale factor and you're squaring it, and that's going to be our area ratio is what we're going to call that. Okay, so let's make a little note off to the side here that this number right here, this is the area ratio, and this number right here, that one is the scale factor. 2 different things. Scale factor is what we call the linear, is the linear scale factor, okay? And this is the area ratio. We have to take that scale factor and square it. Okay, so let's do an example here. It says, if the area of one shape is 100 times larger than the area of a similar shape, then what is the ratio or scale factor of the corresponding sides? So now it's saying, okay, if we had 100, you don't have to write this if you don't want to, but if we continue this table and we got up to 100 for our area ratio, if we went backwards up to our scale factor, what would our scale factor be? Okay, well, we have to go backwards from something squared, and the opposite of squaring something is square rooting. So if we take the square root of 100, that's going to give us 10. That would be your scale factor. Okay, so and it wants us to write that as a ratio, so let's just put 10 to 1. Or you could put 1 to 10, doesn't matter. Okay, because it was our scale factor squared, that would give you 100 times bigger of an area. Okay. All right. So now it's saying if the zoom factor, or also known as the scale factor, zoom and scale factor mean the same thing, is R, then how many times larger is the area of the new shape? So you take your scale factor R and you're going to square it to get your area ratio. So we're going to put R squared right there. That's what we're doing. Okay. All right. Go ahead and flip it to the next page. Let's do some examples with this. Okay, so when you do the examples of these with the scale factor and area ratio, you really have to think about what you're being given and think about, okay, am I squaring it or am I square rooting it? Okay, you got to think about what you're dealing with here, okay? So the two things I want you to focus on each of these problems is think, what is my scale factor and what is my area ratio? Okay, because your area ratio is the square of your scale factor. Okay, so I want you guys to really try these out. Okay, pause this video and see if you guys can figure out these next, or maybe we can do it one at a time. Let's do it one at a time. So go ahead and try letter A, pause this, take maybe 2 minutes. Okay, 2 minutes at a time. Take 2 minutes, try this one out. You need to find the zoom factor and the area of enlargement. Use your book. It tells you what to do. Okay, so 2 minutes. Okay, pause and go. All right, so if you read in the book, it told us that the scale factor, the linear scale factor, was 5. So that was our zoom factor. It was 5. And that means that our area ratio, I want you to write this off to the side here, if you haven't already. That means our area ratio is going to be 5 squared. Okay, and 5 squared, 5 times 5 is 25. So that means that the area of this shape is going to be 25 times bigger than the area of this shape. So we knew the original area was 17. So now we're going to take that times, not 5, take it times 25. Okay, because we're using our area ratio, it's going to be 25 times as big. Okay, so 17 times 25, that is going to give you 425. Again, if that was a little confusing to you, think back to the triangles here. Okay, if it was $2, we're not taking it times our scale factor of 2 to get this price. We have to take it times 4. That's kind of the connection that we're making here. All right, so we get 425. All right, next one. Go ahead, pause the video here and take 2 minutes. All right, so for letter B, we can see we got two distances here. They tell you that the two shapes are similar. It needs to tell you that they're similar, so that way you can do this. So since they're similar, I know that going from 10 to 40, we multiplied by 4. So that's our linear scale factor. So we know our scale factor, that's 4. So that means our area ratio, I'll just write it beneath here. So area ratio is going to be 4 squared, which is 16. So if we want to go from one area to another, we want to multiply by 16, not 4. And this time they gave us the bigger area. So we want to go backwards to the smaller area. So instead of multiplying, like we did in the last problem, going to the bigger one, we want to divide and go backwards smaller. So we want to do 656 is the area of the big one, and we want to divide by 16. to get the area of the smaller one. Okay, and if you divide by 16, you should get 41. So if you got that one right, awesome job. Let's move on to part C here. Move on to part C. Again, take 2 minutes. Ready, go. All right, so for part C, our linear scale factor. Now, if you read in the book, it's comparing the shaded rectangle to the larger rectangle. So if we look at that, the large rectangle, and if you want, you can just draw these separate from each other. That might be a little bit easier to think about. So I'll just show you that really quick. If we draw these separate, so if we were to draw the 2 by 2, comparing it to the 3 by 3, okay, and you want to think about what your scale factor is, right? Well, if this is a distance of 2 and this is a distance of 3, to find your scale factor, you want to divide these two numbers. And I normally put the bigger number on top. Okay, so 3 divided by 2, that's our scale factor. So in our notes here, going from this guy to the big one, the shaded one to the bigger one, it would be 3 halves if you divide that. Okay, 3 halves. Or you could write 1.5 is the same thing. Okay, so that means my area ratio, the ratio of the areas, would be 3 halves squared, or 1.5 squared. Okay, and 3 halves squared, that would be 9/4. Okay, 9/4 or 2.25. Okay, and you can think about this with the boxes as well. Okay, if you look at this area, there's 4 rectangles. So A would equal 4 rectangles, whatever that unit is, and there's 4 of them. And this one, A, is 9. So our ratio, if we take 9 divided by 4, that's your other way of getting your ratio of the areas. You get 9/4. Okay, so there you go. And the last one, this one's kind of a fun one. Okay, it tells you that the 16 by 24 is $800, and he realized that he actually needed an 8 by 12 piece of carpet. Now, intuition is saying, the salesperson is saying, well, that's half the size, right? Our scale factor is 2. So let's just take half the price off, and you'll pay $400. And this is not correct, right? So if we think about this, our scale factor, it is 2. Oh, sorry, if you guys haven't tried this, go ahead and try this out. Okay, try this one out. Pause the video for a minute here. Okay, so our scale factor was 2. That means our area ratio is actually 2 squared, or 4. Okay, so we shouldn't just be taking half the price because we're paying for the area of the carpet, right? So we should be paying 1/4 of the price because this is 1/4 the size of this carpet. So we have to divide 800 by 4. So really this price, if we do 800 divided by 4, it should be $200, not $400 as the salesman was saying. So he was trying to upcharge him here. Okay, let me just draw a visual of that really quick. So if you had that one rug that was 16 by 24, okay, and then you take half of the dimensions. So let's draw a rug that's half the size. So we have 8 by 12. You can see that if we divided this up, this fits in 1/4 of this rug. So we don't want to pay half the price, we want to pay 1/4 of the price. So there's the visual of that. Okay, so that salesman was trying to be sneaky there. All right, last problem, here we go. So this is from this is using that formula from yesterday's lesson. Okay, we're taking a look at two similar hexagons, and we're going to compare the areas. So it wants you to find the area of both of these hexagons. Okay, so pause the video here. Actually, before you pause, let's remember our formula from yesterday. So if we find a place to write this, maybe at the bottom down here. So the area of your hexagon, or area of any regular polygon, is 1/2 SAN. And by the way, I kind of rushed through this yesterday. The S, I put a little hook at the end of it, just so that way it doesn't look like a 5. Sometimes S's in math look like 5s. Okay, so this S stands for the side length. Side length, which you're given here. This is the side length. A stands for apothem. And N stands for number of sides. Okay, so in this case, these are both hexagons, so that's going to be 6. And it gives you the side length. So all you guys have to do on these ones is you have to find the apothem. And remember, the apothem is that little line segment from the center of your shape perpendicular to any of the sides. That's the apothem. So you want to find that length and then just plug it into your formula. Okay. Maybe let's find the first one together. So for our work, let's find the area of this first hexagon. Okay. So remember, the way to do this, you want to divide this up into equilateral triangles for a hexagon. So there's 6 of them. So if you divide that up, there would be 6 congruent triangles there. And we're going to find the area of one of them and then multiply it by 6. Okay, or your formula takes care of that for you. So let's go ahead and draw that triangle that we have there. Okay, maybe draw an arrow to it. Okay, so we know the bottom side is 10. We are trying to find the apothem A. So if we split this in half, now if you remember how to find your angle, you'd want to find the interior angle, so you'd want to use that interior angle formula. Hopefully you have that one memorized by now. You've been using it in the homework and such. Okay, you've got each angle in regular polygons. The interior angle is this formula. Plug in 6 and you should get 120 for a hexagon. So that angle right there is 120 degrees. Okay, so if we split that in half, remember all of these bisect those angles, so half of 120 is 60. So that little angle right there, and in this triangle here, is 60 degrees. So now let's draw that half of the triangle. So this is a 30, 60, 90. That's why hexagons are so great, okay, because you can just divide this into a 30, 60, 90 triangle. And if we take half of 10, that's going to be 5. And now with our 30, 60, 90 right triangle, think about it a second. You can probably guess what this side's going to be. It's going to be 5 square root 3 from our special right triangles. Okay, remember it's up on that wall, okay, under a special right triangle. So 5 square root 3. And this would be 10, by the way, because it's an equilateral triangle. Okay, so that's how that works. So now we have our A value. So this is equal to A. Now you have everything you need for your formula. So let's find the area. So area is going to be 1/2 of your side length S, which in this case is 10, times our apothem, A, which is 5 square root 3, times N, number of sides is 6. Okay, and if you multiply that all out, half of 10 is 5. 5 times 6 is 30. 30 times 5, that'd be 150. And then we still have that square root of 3 in there. Okay, and now I would type this into your calculator. And if you type that in, you should get, I've got 259.8 square units. Okay, so there's one of your hexagons. Okay, now I want you guys to do this again, but now, let's see, what is it asking us? Okay, let's answer this one up here. It says, how will the area increase? Well, our scale factor, let's write that down. Scale factor, you guys can find that. Find your scale factor, and then write down your area ratio. Okay, so if we look at our scale factor going from 10 to 30, well, that's going to be a scale factor of 3. 10 times 3 gives us 30. So that's our scale factor. That means our area ratio should be our scale factor squared, right? If we take our scale factor 3 squared, that should be 9. Okay, so we want to check and make sure that it works. So we know our area of the small hexagon is 259.81 or 259.8, and the area of the large hexagon should be 9 times as big, but let's check and find out. So I want you guys to practice. You really need to practice doing this area formula. So use this extra space here and find the area of the large hexagon over here. So do the same thing, but now you've got 30. So do the same thing, but now you have 30 in the bottom. Do the exact same steps that we did over here. Okay, and see what the area of the large hexagon is. So pause, and then we'll finish this up. All right, here we go. So if you split up your triangle, you should have had 15 in the bottom here, and your apothem 15 squared root of 3. So that's actually all you needed. You have your side length now, you have your apothem, and then you just have to plug that into your formula. Okay, because again, this was a 30, 60, 90. So now our area, you should have 1/2 SAN, so 1/2 of your side length, which was 30, times our apothem, which is 15 squared root of 3, times your number of sides, which is still 6. Okay, now if we do that, half of 30 is 15. 15 times 15 is 225. Times 6 is 1,350. And you still have square root of 3. And now if you type that in your calculator, that gives you approximately 2,338.27. Or we'll go 0.3. So now, to double check, if you divide these two numbers in your calculator, hang on one second. If we grab our calculators here and we divide that, so we got 2,338.3 divided by 259.8. This should be the area of our ratios. It should be approximately 9. It's not going to be exact because we rounded, but it should be close to 9. Okay, and there you go. It's like 9.000, so it's close to 9. Okay, so that's how it works. We double checked it. All right. Nice job, guys. Okay, the rest of your time, work on your homework. This homework's not going to be due till Monday since we have a double lesson homework. Okay.